And the next two speakers are Christopher Miller and Yilser Kabaran, who are part of the BlueSat project and the Bluton rover project at UNSW. So these are a bunch of undergraduate students who are building satellites and rovers. So welcome, Christopher and Yilser.
Oh, we good? Hopefully it works. Fantastic. Does this thing work? Yep. Oh, great. So hello, I'm Chris, and this is Yilser, and as you just learned, we're from BlueSat. We are working on rovers. So what BlueSat? Oh, first off, why rovers? What are we doing? Why this? So currently, as most of you know, rovers are used for exploration. Use them a lot to look in, look under rocks, and not look into rocks, and to do and see what's going on. But really, in the future, we're learning now that robotics is becoming a lot more of an assistance role. They're helping humans do their job, do it better, more effectively, and that's what we're trying to really learn about, is how to assist humans on kind of missions doing what they're trying to do, be it getting tools, repairing objects, doing sample studies here and there. Yeah. So who is BlueSat? So we're a bunch of undergraduate engineers. Really what we are is a safe place for people to come and make mistakes. We all make mistakes, we make a lot of mistakes. We get a lot of things wrong. So we're just learning how to do things better and how to understand, how to analyze systems and build them and do it effectively and enhance the overall performance of what we're making. Yeah. So we build rovers, that's what off-road robotics is. So this is our rover. This is our first real rover. We made one before, and it was effectively just a box with wheels and a lot of computer guts. Now we've really drilled down into the mechanical systems, trying to figure out how to make a system that can go over rocks and do a whole bunch of things. It doesn't, forewarning, but we try. So mechanical inspiration. I'm part of the mechanical side of things. So we use a lot of NASA systems, a lot of their rovers, looking at how other organizations that have a lot more experience tackle these kind of things, as well as how you dig things into the diggers, linear actuators, that kind of stuff, is how to actually get soil out of the ground to analyze it. So we have several major systems. We have the rocket bogie suspension system, we have an arm, we have a wheel housing, and we have a lightweight, rigid structure. And the beauty of this is that it all flat packs. So if one of our challenges we have is we go overseas to compete in challenges, so this thing has to be put in a suitcase in the airplane hold. So we can take it all apart, it all flat packs down, get there, put it all back together. It's really fun experience. But it says rigid. It's not actually very rigid. We tried, but didn't do it very well. So here's our rocket bogie and the differential. Here's our arm. It says claw. We have a claw, but I forgot to put a photo of the claw in. Apologies, everyone. And I'll hand over to Yilser now for the software side of things.
So our system is based off ROS, Robotic Operating System. The name is quite a lie. It's not a robotic system, an operating system at all. It's a nice little message transfer system for modular nodes for programming. So we can build our robot with our base stuff for like driving and arm and the like. And if we design any other components, we just hot swap software in and out, and works flawlessly most of the time. Our own custom interfaces like will boot up. As you can see, one of them there, one of the earlier betas of our interfaces, and it's all interfacing with a nice little control board we've designed in-house, which works. You'll find out later what didn't work, which is fun. So all our comm stuff works over generic Wi-Fi, or we're used to. We managed to get about a K range out of the system, which we're quite happy about in test conditions. We have a nice little control package, sensor package with camera, GPS, compass, all the guts you need by default for autonomous rover, which worked pretty well. And I managed to get a LiDAR integrated with the system, which got somewhat working with autonomous navigation purely off vision alone, which was nice. Our electrical system, as I said before, our own prototype boards done in-house for power regulation, the sensor inputs and the like, and control systems. Yep. So we made a robot. What do you do with it? Obviously, put it in a suitcase, fly over to Poland. Yeah, natural first response for that. So we entered in the European Rover Challenge. Over 40 teams from like everywhere on the world competed. We were the first Australian team to ever enter the thing. One of the first Southern Hemisphere teams to enter ever as well. Achieved 15 out of 40, which we thought was okay considering we caught fire about halfway through and couldn't compete in the second half, so pretty solid attempt. So this competition was more of the field tasks that you'd encounter, maintenance of your generator or the like if you're like on Mars and generator's blown and you don't have life support, send out the rover. Recover science payloads, dirt samples or the like. Assistant task in retrieving equipment, and blind traversal, which was what we needed the LiDAR before, getting over obstacles and the like. With no camera feedback, half our sensors gone, we're relying purely off like laser data or something to try and navigate. There were some interesting crashes in that.
And there's several roles.
Three rolls? I don't know. But yeah, so there we have a rover. Great, what do we do with it? Well, we're gonna modify the thing, so less rolls, better sensors and the like, and move towards more of a scientific analysis and testing for other payloads and the like. So we've got it's a base system. It runs, it goes where it needs to go most of the time, fixing where it can actually go. Or we're moving on, working with other groups, trying to get our other scientific sensors worked out. We know there's another group working with low-cost in-house spectral cameras or something of the like. Start testing those out in the field, getting some better data, using this for a nice science retrieval vehicle. And also, while we're building this up to be more off-road ready, we're building a new rover over the next 2 years that will hopefully get over all the challenges that we've encountered over this time and head back out into international competitions and probably do better than 15th, probably without fires. And we'll see. And that was it. Yeah, that's it.
Questions?
Have you talked to any of the Australian mining companies about whether something like that rover would be useful for mine safety or investigation once you get the setting itself on fire by themselves?
Yeah, that's been our biggest goal is to first to make it work and to make it work reliably, and then to try and figure out how to use it. So be it doing biological sampling or mine investigation, all kinds of stuff. But yeah, there's thought about it, but no action as of yet. We haven't
Talk
informed
to
us
the
before.
potential customers now,
Okay.
because they might go, their students are cute and give you money.
Networking opportunities.
Yeah. It's easy now we have a rover, because before it was, we're going to do something, can we have some money? They're like, no, just go away.
Like a terrible rover.
Okay. Will do.
Any other questions?
How do you plan to solve the rigidity problem?
So there's several ways around it. Really, the biggest thing that we overlook is that we use a skid steer as well as a rocket bogie. So a skid steer is you need a very rigid structure to use that, and a rocket bogie is by its very nature not very rigid. So really, the way we're going to look about doing it, first of all, we're not actually using the rocket bogie. We're going to just start investigating other avenues, because again, these systems are designed for very low speed. Odd environment, not these high speed, go there, pick up a tool. It's not really the right system. So moving away from that, but how do we settle on that line? It would be just really go back and doing probably more analysis, trying to figure out more of the characteristic motions of the system, as well as using thicker. The biggest part was we used very thick standoffs, and that was the worst part of it. We used very thin standoffs, and they weren't able to take the load in the flexure. If we use a fatter standoff, we can really mitigate all those problems. But we actually haven't tested that. It's just more of a discussion point. Yeah.
All right. Okay. Thank you, Chris. And
Great.
it's not the first time Australia has crashed a European contest either. That's